This dashboard displays the immediate economic yields of India's E20 mandate. By blending 20% ethanol into the national petrol supply, the government has realized an estimated 1.97 lakh crore rupees in foreign exchange savings, alongside a reduction of 952 lakh tons of carbon dioxide. But when we map where these savings are generated, the economic victory intersects with severe environmental stress. The highest concentrations of ethanol production sit directly atop the nation's most critically depleted groundwater reserves. We are looking at a national energy policy that executes flawlessly on an economic spreadsheet, while simultaneously driving a localized resource crisis. Ethanol itself is neither an absolute climate savior nor a universal environmental hazard. Its viability is strictly conditional. It depends entirely on three physical constraints: the exact crop used to produce it, the mechanical compatibility of the hardware burning it, and the hydrological zoning of the region growing it. To understand how a single molecule can solve an energy crisis while creating an agricultural one, we have to trace its path from the combustion chamber all the way to constitutional law. Because treating energy policy purely as an economic equation, without accounting for physical and chemical realities, consistently engineers a devastating secondary crisis. To see why refiners and governments are pushing so aggressively for this fuel additive, we have to look at the chemistry. This chart plots fuel blend stocks, measuring their anti-knock index against toxicity. Ethanol stands out as an effective, non-toxic octane booster. This creates a massive economic incentive. Refineries blend cheaper, lower-octane subgrade gasoline with incremental ethanol, hitting legal final octane requirements at lower cost. This simple chemical advantage, boosting octane while cutting costs, is the actual driver behind aggressive blending mandates globally. But the same chemical structure that makes ethanol blend perfectly with gasoline also gives it a high affinity for water. Ethanol is highly hygroscopic. It actively pulls moisture from the surrounding environment, introducing severe operational constraints if the system holding it isn't specifically designed for it. The exact chemical properties that make ethanol an ideal modern fuel additive simultaneously make it a destructive force when injected into incompatible older environments. When E20 fuel enters a legacy vehicle built before 2023, the fuel absorbs water, separates, and initiates a cascade of chemical reactions against untreated metals. Engineers refer to this specific failure mechanism as stress corrosion cracking, a condition rapidly accelerated by the water separation found in E10 and E20 blends. These three carbon steel test coupons demonstrate the progression. The surface pitting increases aggressively from left to right after exposure to ethanol blends. Over time, this corrosion inevitably advances. Looking at these cylindrical components, the untreated metal in stages 3 and 4 is heavily compromised by flaky rust and severe oxidation. Inside highly sensitive engine internals, the damage is microscopic but structural, as rust-colored spots pit the inside surface of the stator. For the millions of citizens driving pre-2023 vehicles, this translates directly into decreased mileage, failing fuel pumps, and voided warranties. Imposing a modern chemical mandate on a legacy mechanical fleet effectively transfers the financial cost of national decarbonization directly onto the consumer through engine degradation. But mechanical friction is small compared to the agricultural scale. To grasp the sheer volume of feedstock required, we must move to the fields. India's ambitious blending targets rely overwhelmingly on first-generation feedstocks, primarily sugarcane. This stark bar chart visualizes the staggering hidden metric behind that reliance, the virtual water footprint. Producing just a single liter of sugarcane ethanol requires upwards of 3,636 liters of water. To be clear, this footprint doesn't measure the highly efficient process water recycled inside a modern distillery.
It measures the immense volume of irrigation water consumed in the field to grow the crop in the first place. And that massive water extraction is highly concentrated. India's ethanol capacity is heavily clustered in specific administrative units, like the chronically drought-prone Marathwada and Vidarbha regions of Maharashtra. We are pitting the immense thirst of industrial sugarcane against the physical reality of a severely fractured, parched landscape. Hydrologists describe this dynamic as the virtual export of groundwater. The region utilizes its scarce local irrigation to grow a water-intensive cash crop, converts it into an alcohol fuel, and physically ships it away to power vehicles in distant, heavily populated urban centers. This is a direct deprivation of resources, where industrial fuel crops actively compete with local drinking reserves. Scaling sugarcane ethanol in water-stressed regions is not a sustainable climate solution. It is a mechanism that trades immediate citizen water security for national fuel security. To mitigate this severe water crisis, recent policy incentives have driven a massive shift toward an alternative feedstock, maize. Driven by higher, guaranteed offtake prices from oil marketing companies, maize cultivation has seen explosive, heavily subsidized growth. But this line graph tracks the resulting secondary crisis, the fuel versus feed displacement. As maize acreage expands, farmers abandon foundational crops, causing a steep decline in pulses and oilseeds. The economic survey flagged the macroeconomic consequence. India is now forced into an increased reliance on foreign edible oil imports to cover the domestic shortfall. The downstream impact hits the domestic poultry and cattle industries just as hard, starving them of the affordable maize supplies they rely on for feed. Without strict national feedstock zoning, agricultural markets will inherently prioritize subsidized energy demands over food security, engineering dangerous price volatility in the process. Zooming out from the agricultural data, this resource displacement elevates into a profound legal tension for the state itself. At the heart of the ethanol paradox is a direct constitutional conflict between two fundamental directives, Article 39b and Article 21. Article 39b validates and mandates the state's imperative to manage material resources to secure national energy independence and strategic self-reliance. But constitutional jurisprudence has expanded Article 21 to strictly guarantee citizens their fundamental rights to safe drinking water and food security. When the state licenses high water footprint distilleries in officially overexploited groundwater zones, it represents a direct violation of the Public Trust Doctrine, which requires the state to protect natural resources for public use. An energy policy that achieves decarbonization by draining the foundational water and food reserves of its own citizens is legally and constitutionally untenable. The resolution to the ethanol paradox is not to abandon biofuel policy entirely. The data dictates a strict evolution of the feedstock. To reconcile this conflict, there must be a vital, mandatory pivot to second-generation, or 2G, cellulosic ethanol production. Instead of consuming human food supplies, 2G ethanol functions by extracting necessary alcohols from unusable agricultural residues, like rice straw and bagasse. We already have real-world operational proofs of concept, like the Bargar biorefinery, proving this transition is physically and economically possible at an industrial scale. This specific technological shift successfully decouples the chemical octane and emissions benefits of ethanol from the sensitive water and food matrices. Ethanol is a brilliant chemical tool, but it is currently being wielded with a blunt first-generation policy mechanism. True national energy security cannot be legislated in an economic vacuum. It requires an integrated governance model that perfectly aligns chemical engineering with hydrological reality and constitutional human rights.